Hello everyone and welcome to this new video. This is the third part of the embedding. The first two we saw the theory and then the math, and now we have to apply what we learned. So instead of just importing pre-made libraries or models, I decided to build a Word2Vec model entirely from scratch using PyTorch. So the goal isn't just to make it work, but to implement the raw math calculating gradients manually and writing my own optimizer to to prove that I understand exactly what's happening under the hood. Okay, so the first thing, let's run the library cell. We wait for it to connect to the T4 GPU. Okay, let's see. Okay. Now, for the data, so I've used the text8 dataset, which is like essentially 100 megabytes of cleaned Wikipedia text. The raw data is just a massive string of like 17 million words. This is the source of the data. Let's load it. Like common words in Wikipedia like the, and, like of appear millions of times, but they don't carry many meaning. But so if we train on them too much, they drown the signals from important words. So I implemented subsampling here using the drop probe. This probability formula aggressively deletes frequent words, leaving us with the training set of about 8 million high-quality tokens focused on semantic meanings. Okay, once we've done that, let's run the cell. Okay, for the model architecture, this is where we start the hard code. Most people would use the nn.linear layers here. I didn't. I manually initialized two massive matrices, W in and W out. This is the input vector, and this is for the context vectors. So we're training 50,000 words with like 100 dimensions each. I used Xavier initialization, scaling like by 1 divided over the square root of the embedding dimensions to ensure that our gradients didn't vanish or explode right from the start. So it's just like a control. We can see an image of the architecture. You can pause this video here and read all of this. Okay, now for the training loop. Let's run this before. Okay. For the training, this is the heart of the project. I'm using the skipgram architecture, where we take a center word and try to predict the words around it. We've seen this in the theory part, also in the math. There are two major optimizations I had to implement manually here. So negative sampling, calculating the softmax probability for 50,000 words is computationally impossible for every step. So instead, I maximize the probability of the real context word and minimize the probability I chose 10 negative or random noise words. You can see the manual log sigmoid loss calculation here. I've also implemented a manual add a grad, so I'm not using the torch.optim for optimization. I wrote the add a grad update rule from scratch because the text data is sparse, so some words appear rarely, and the add grad adapts the learning rate for each individual parameter, taking larger steps for rare words and smaller steps for frequent ones. This is very crucial for the model to converge. So let's run this important part. Okay, the model is learning. Okay, so now since the model finished the training, it took about 1 minute. We only used 5 epochs. 5. So we can see the loss function decreasing. Now let's test it. So after training, hopefully the model learned to map the words into the vector space. We can prove this with vector arithmetic. Classic test is can do a king minus man plus a woman. Let's try. So we've got this output. So these words should be close to these words here. We can check the meaning on Google. Okay, so the person who inherits and continues the work of a king. Emperor, it's close to king. In this case, this is also a country, so it picked up that we're using countries here. Let's see this word. This is a rank of a person. I don't know if it's related here. Here we can see, like, this is a proof that our model at least learned the minimum from the data. Like he minus him plus she, it's her. Again, this is also close, his. And I don't know about this nomination. Again, we've used like 1 minute of training. So it's pretty good, the result. This is also an interactive demo where we ask the user to enter a word and hopefully you get close words. Let's type in kink. Okay, prince, throne. Very excellent matches. Let's say Paris. Hopefully this is related to Paris. Something historical, I don't know. Let's do one last example. Germany. Okay, it picked up that it's a country and these are like countries, which is pretty good. Not perfect. Let's stop it for now. Okay, so we can see that we successfully implemented the Word2Vec model. In practice, we use like pre-made tools and libraries, models on Hugging Face, etc. They are more computationally efficient scalable, and everything is better. But we just did this so we can better understand the math and the architecture behind the embedding. So thank you for watching.